Have you ever just stopped to wonder how your computer knows if one number is bigger than another? I mean, it seems so incredibly simple, right? But that one decision is at the absolute heart of everything, from sorting a playlist to landing a rover on Mars. Well, today we're going to pull back the curtain on the magic behind this fundamental decision, the digital comparator.
Seriously, think about it for a second. At their core, computers are just this massive collection of switches that are either on or off, a 1 or a 0. So how do they get from that simple on-off state to doing something that feels like thinking, like making a choice? That's the exact question we are going to dig into right now.
And the hero of our story is this, the comparator. It's a special kind of digital circuit called a combinational circuit. Now think of it like a basic calculator. You put numbers in and you instantly get an answer. Its output depends only on the inputs you give it right now, with zero memory of what happened before. Its entire job, its whole purpose in life, is to take two numbers and figure out how they relate to each other.
And it takes all that potential complexity and boils it down to one of three incredibly simple yet profoundly important answers. These three outputs, they're the absolute foundation of all decision-making in the entire digital world.
And that's it. Is the first number bigger? Is it smaller? Or are they exactly the same? Every single decision-making process inside a CPU, from sorting a list of songs to performing complex calculations, ultimately comes down to asking these three fundamental questions over and over again.
So, here's our roadmap for this little deep dive. We'll start with the basics. Then we'll break down the absolute simplest comparator you can imagine. We'll see how it's actually coded, figure out how to scale it up for bigger numbers, and finally, we'll see why this little circuit is so critical in all the devices we use every single day.
All right, let's get into it. The idea itself is pretty straightforward, but comparators actually come in two main varieties, each with a slightly different job to do.
So on one hand, you've got the equality comparator. It's basically a yes or no machine. Its only job is to answer one question. Are these two numbers identical? But then you have the magnitude comparator. Now this one's the real powerhouse because it gives us so much more information. It doesn't just check for equality, it tells you the whole story. Greater than, less than, and equal to. And because it's so much more versatile, we're going to be focusing on the magnitude comparator for the rest of this explainer.
You know, to really understand how something complex works, you have to start small. And I mean as small as it gets, comparing just a single bit to another single bit. This right here is our fundamental building block.
Okay, now this truth table, this is where the magic really starts to take shape. It's a complete map of every single possible outcome. Let's just walk through it. If A and B are both 0, well, they're equal, right? So the A equals B column gets a 1. Makes sense. If A is 0 and B is 1, then A is less than B. If A is 1 and B is 0, now A is greater than B. And of course, if they're both 1, they're equal again. It's just simple, pure logic, and it gives us everything we need to build a circuit.
And let's be clear, this isn't just a chart for us to look at. This truth table is the actual blueprint for our circuit. By looking at exactly where those ones show up in the output columns, we can write the precise mathematical logic that the physical circuit needs to follow.
And here's how that blueprint translates directly into the language of logic gates. The A's greater than B output is only a 1 when A is 1 and B is 0. A is less than B is only true when A is 0 and B is 1. And what about equality? Well, they're equal when they are the same, a job that's perfectly handled by a logic gate called an XNOR gate, which outputs a 1 only when its inputs are identical. This is digital logic in its purest form. It's beautiful.
Okay, so we've got the theory, we've got the logic, but how do we actually tell a computer chip to build this thing? Well, we use a special kind of programming language called a hardware description language, or HDL. You can think of it as a blueprint written in code. And one of the most common ones out there is called Verilog.
Now, in Verilog, there are two main ways to describe our comparator. The first is called data flow modeling. This is a very literal translation of our Boolean expressions. You can see it right there in the code. Assign A greater than B equals A and not B. That literally means A and not B. The other way is behavioral modeling. This is a bit more abstract. It's more like writing software, where you just describe the behavior you want. If A is greater than B, then do this. It's usually a lot more intuitive for people to read. Now, you could absolutely write out all that logic by hand, and for learning, it's a fantastic exercise. But in the real world, engineers have a much cleaner, much more powerful tool at their disposal. And here they are, relational operators. These guys are built right into the language. So instead of manually piecing together all those logic gates, you can just use the symbols you already know.
greater than, less than, and, this is key, the double equal sign for comparison. The real magic here is that a program called a synthesis tool takes your code and automatically figures out the most efficient way to build this logic using the physical gates on the chip. It's incredibly elegant and super efficient.
All right, so we've completely mastered comparing a single bit. That's great. But our computers work with numbers that are 8, 16, 32, or even 64 bits long. So how do we scale our simple little logic block up to handle real-world numbers?
Well, the algorithm is actually identical to how you and I compare numbers in our heads. You start from the most important digit. In binary, that's the most significant bit, or MSB. If those bits are different, you're done. You instantly know which number is bigger. But if they're the same, you just move one position to the right and you repeat the process over and over until you either find a difference or you run out of bits.
And the absolute beauty of modern hardware description languages is that you don't need to write a whole new circuit for a 2-bit comparator and a 4-bit and an 8-bit. No way. You write a single, flexible module, and you use something called a parameter to define how wide you want it to be. This is how pros design hardware. You make it reusable and scalable right from the start.
So we've gone from a single bit all the way to a powerful, scalable design. Now let's tie this all back to the real world and see where these comparators are the unsung heroes inside the tech we use every day.
They are literally everywhere. I mean, they're a fundamental piece of the arithmetic logic unit, the ALU. That's the mathematical brain of your computer's processor. They're also essential for any circuit that needs to sort data, for managing where things are stored in memory, and even in systems that check for errors in data. Basically, anywhere a digital system needs to make a decision, you can bet a comparator is doing the heavy lifting.
So if you take anything away from this, remember these key points. A comparator is a simple circuit that answers a simple question about two numbers. We always start with a truth table to define its logic. We can then turn that into Boolean algebra, but more practically, we use the built-in relational operators in a language like Verilog. And if you want to design like a pro, you always make your designs scalable.
And I'll leave you with this final thought to chew on. We've seen that at its very core, a computer makes decisions using this incredibly simple logic. So now that you know how it works, start looking around you. What else in your world, from your phone's interface to a traffic light controller, is ultimately just a massively complex system built on countless tiny decisions of greater than, less than, or equal to?